Well, thanks for joining me this afternoon for the second in this three-part series on climate change issues. Today, we're going to look at Rogue Valley climate trends and projections and why we care. This is the outline of the talk as we're going to work our way through it. We're going to start with a little discussion of why we have confidence in the climate models. Then we'll have a very quick look at what models suggest globally and statewide for our future. Then we'll look at local climate history, local trends, and I'll close with a why we should care about all this. So let's start from the beginning. The term GCM stands for Global Climate Models, but conveniently, it also refers to general circulation models. And one of the things that often happens is folks find themselves questioning whether the climate models are really credible. And that's a reasonable question. But fortunately, because we've had climate models for several years, it's been possible to test them, not only against what's actually happening, but also to test them in a different way, and that is to run the models backwards, really, over the period of time for which we have global temperature records, and see if the global models, as we run them forward, actually show the kind of data that we find, and when we look at the actual records, constitutes a pretty good test of whether we should trust these models into the future. We can run them two ways. And this is the key to the test of credibility. The first way is to run the models backwards, if you like, with human emissions included. That's human emissions of greenhouse gases included in the model. And the second way to test them, or the second part of the test, I should say, is to run them backwards, but eliminate human emissions of greenhouse gases and include into the models only the natural influences that we know influence global temperature. So let's start by looking at global models, and what we're going to do is run them backwards. And as we look at this, I want to point out that the baseline, the zero value in this illustration, in this graph, is in fact the average for the period 1901 to 1960. And what you can see is if we go back in time, everything is below the line, and as we go up to the last 60 or 80 years, everything pretty much is above the line. The important point about this chart is that we are looking at observed data, and you can see there are three colored lines, the blue, the sort of red line, and the black line, and these are observed data, firstly from NASA's Goddard Institute for Space Studies. That's the first one. The second one, HATCRUT, is the actual observations as they are tracked from Britain, from the British Met Office and University of East Anglia's Climate Research Unit. And the last one are the data as compiled by NOAA. The orange array and the orange solid line represent the models, and these are models using what I'm going to talk about in a few minutes, the representative concentration pathway 8.5. And the key idea to focus on here is, I hope you can see my little cursor, you can see that the actual data follow pretty closely along with what the models suggest that the temperature should have been, looking at the variables that are included in the models. And so, in fact, what we see is in several of the observed data sets, the actual data are above what the models predicted. And that runs up until 2000 and about 17. The second test is to take out those human emissions and just look at what happens if we only look at natural influences. And again, you're looking at those three colored lines, which represent observed data. And the blue, dark blue, is the mean of the models with only natural forcings, natural factors influencing them. And what you can see here is, as we run backwards, If we don't include the human emissions, the models give us a line which is very different from what we've actually seen. In fact, it gives us a line which is sort of on average about flat. And what these analyses suggest to us is the models do a pretty good job of running backwards, and therefore we should have some confidence in what they are predicting about what happens into the future. The important point about models to remember, and I'm just going to quickly run through this one. This shows you that the same thing is true across the planet, showing that that those models do a pretty good job wherever we apply them, so long as we include human emissions of greenhouse gases. What we're going to look at is what it is that folks include in their models. So these models are based on what's called the representative concentration pathway, which stands for the representative concentration of greenhouse gases in the atmosphere. A value of 2.6 for the RCP means that we pretty much cease emissions right away. At the other extreme, there's the RCP 8.5, which has come to be called the business as usual model, and I'll show you why that is in just a minute. When this was developed, it was actually supposed to represent a very extreme condition wherein we did nothing to address greenhouse gases. There are intermediate values. There's an RCP 4.5 and an RCP 6, and what they represent is human activity being reduced substantially, so that the line of accelerating greenhouse gas emissions, fossil fuel use, is slowed considerably. So those are the four models, and then when we look at the pattern on the right, you can see what they should suggest by 2100. RCP 8.5, which, as I will talk about in a moment, the business as usual model, suggests that by 2100 we should be about 4 degrees, assuming we continue what we're doing, about 4 degrees centigrade above the actually the 1981 to 2000 average, which is what the zero is there. What we're doing now is asking the question, because it's often suggested, asking the question, what's been happening to actual data in relation to the models? What we're looking at here is data from NASA, and we're comparing those to the models using the representative concentration pathway 8.5. Remember, this was initially described as the worst case scenario, but seems to be more like the business as usual scenario. And the reason it's called business as usual is because this is exactly the trajectory we're on. You can see that the red line here represents the actual data from NASA, the Goddard Institute for Space Studies again, whereas the blue represents the models. And there's a range in the models because not every organization that runs the models gets exactly the same answer, because they have slightly different variables in their models. And what we can see from this is whether we look at the monthly data on the left or the annual data on the right, we get the same indication. This chart illustrates what's been happening to the sea ice extent at its minimum. Polar Arctic sea ice goes through an annual fluctuation. During the winter, it's high. During the summer, it's low. This represents the minimum. And what you can see here, the brown color represents what's actually been happening up until 2019, whereas the black line represents the average of what the models suggested should be happening to sea ice extent. And what we find is the sea ice at its minimum is actually declining much more rapidly than the models suggest. What we're looking at here is actual sea level rise, the satellite observations, and then earlier the tidal gauges, which are mounted on land, and the IPCC projections. And what we find is that the actual data are at the high end of what the IPCC projected they should be. What these data collectively suggest is the models are pretty sound in terms of they actually reflecting what we historically have seen. And not only that, that RCP 8.5 scenario seems to be the scenario that we're on. So now we have a quick pause for questions.
Yeah, we haven't got any questions in the chat or the Q&A.
Okay.
For the participants that are listening right now to the presentation, if you have any questions, feel free to type them in the Q&A box. And
Okay.
Dr. Allen,
So if we need to, we can take a longer break next time.
Yeah.
If we get some questions in.
Why don't we do that?
Okay, that'll be fine. Thanks, Carrie. Okay, so the second question I'm posing myself is, what do the models suggest globally and statewide our future temperatures will be? So let's take a quick look. Well, this is very similar to the data set you just saw. These look at the four representative concentration pathways from 2.6 up to the 8.5. These take us up to 2100. One of the interesting factors about the Intergovernmental Panel on Climate Change last edition that came out 2013-2014 is that they went beyond 2100. Up until that time, models generally took us to 2100 and didn't go beyond it. When that last IPCC came out, they took us to 2300. But what you can see here is the same approximate value that I suggested a moment ago. Globally, by 2100, that RCP 8.5 scenario looks as though it's going to give us about a 4-degree centigrade temperature increase. And if you don't do a quick conversion, 4 degrees centigrade is a little under 9 degrees Fahrenheit. It's about 8 or so degrees Fahrenheit. But we can go on beyond that. It's actually looks about 7.2 degrees Fahrenheit, according to this array, which I put on the graph, so it must be right. Now what we can do is look beyond 2100 with those models, and we go up to 2300. Now, the models that go up to 2300 are not the same models, all of them that did the calculations up to 2100, then you can see the number of models that were being run in this test as the numbers right above the graph. And what happens is by 2100, the number of the actual identity of the models changes, and so the lines are slightly different. So there's this break at the year 2100. They're slightly different from there forward. And what you can see is, if we look forward to 2300, we're looking, if we follow the 8.5 scenario, we're looking at something like a 14-degree Fahrenheit increase, which could be even worse than that. You can see the range goes from probably something like 6 up to 21 degrees or so Fahrenheit. So the dark blue line at the bottom there is the best case human response scenario. That basically assumes that at the time that I finish this presentation, we immediately stop emitting greenhouse gases. We can see right away that that's not going to happen. So that is called the unavoidable depiction of future temperatures. Up the top end is what's called unmanageable, because, and I'll explain this a little more at the end when I talk about why we care. But at that end of the range, the 8.5 RCP, by 2300, there will be all manner of calamities which will have befallen us long before that happens, as I will explain later. Global projections also include other variables beside temperature. The global projections for precipitation are very variable around the planet. Generally speaking, what we can say is that areas which are currently dry are likely to be drier as we go into the future, and areas that are currently wet are likely to be wetter. That's a very, very broad generalization, however. Let's have a look at Oregon. Fortunately, in Oregon, we have an organization called the Oregon Climate Change Research Institute, which is based in Corvallis at Oregon State University, and they keep us up to date on what the projections are, and they're excellent organization if anybody's looking for information on climate impacts in Oregon. They come out with a report every 2 or 3 years. What we're looking at here is data compared now to the baseline of 1970 to 1999, and that's set at 0. What you can see that historically, if we go back well into the last century, the temperatures are on average below that average. But as we go forward, this data set only, these models only give us projections up till 2100. What you can see here is patterns which are basically similar to the global patterns. If we follow the RCP 8.5 scenario, you can see we're going to be at about 8 degrees Fahrenheit warmer than that historical average. And if we look at precipitation, what we find is an interesting pattern. I'm going to come back to these patterns when we get into what's happening locally. But what you can see is, as we go through the century, the range of data that the models project are very broad, and so the dark blue line represents the average of the models. And what you can see is it seems as though maybe it's going up just a little as we go through the century. I spent a lot of time playing with statistical data sets, and I would say that the difference between that line and no increase at all is probably not significant. So I would look at those data and say, I doubt that that's a significant change. This is Oregon precipitation coming from the US Geological Survey, and they've run some 28 models. The black line represents the historical pattern, and then the red and the blue line, as you can see on the bottom left of that graph, represent the red is the RCP 8.5 projection into the future, and the blue represents the 4.5 projection. And what you can see here again is maybe a slight increase as we go through the century, but essentially I would say probably none. Also, the thing that really is worth looking at is how the lines vary. So what you can see is, and this is pretty much whether we look at the red line or the black line, what we can see is that the troughs and the peaks are more extreme. And what that means is that the high points represent increases in precipitation, and the low points represent decreases in precipitation, which we would otherwise know as droughts. What we're looking at here now is snow. The upper graph is overall precipitation, which includes snow, hail, and rain. The lower graph looks at Oregon's snow. And what you can see again, as the black line represents a history of decreasing snow since about the 1970s. And what's interesting is, whatever data set we look at, we find that the basic impact of global warming, the climate impacts of global warming, really start around the 1970s and pick up. And as we go into the future, you can see they get really quite dramatically worse, such that by the end of the century, and we'll come back and look at this in relation to Jackson County in a few minutes, what we can see is the amount of snowfall is going to decrease across the state substantially. And that's whether we look at the worst case scenario, the RCP 8.5, or we make the assumption that we are smarter than that and we reduce our emissions of greenhouse gases substantially. Either way, snowpack is going to be declining. And that's particularly important because in Oregon, throughout the Northwest, Pacific Northwest, what we have done is, instead of building many dams, what we do is rely on the snowpack at a high elevation to gradually thaw out during the summer and provide us with irrigation water and provide the streams with water through the summer and into the fall. And so this is really going to be a problem as we go through the century, assuming we do nothing to address the problem of greenhouse gas emissions. There are a couple of other patterns that are worth looking at. The previous charts looked at mean annual precipitation, but that's not all that's important with precipitation, particularly rainfall. There are a couple of other things that are important about it. One is, what season does the rain fall? And what we can see here is a sequence in which we're looking at winter, spring, summer, and fall. And I just put a little red circle around where we are. And what you can see is winters are likely to be just a little wetter. When we look at spring, then what we find is not much different from historical patterns. But what's particularly disturbing is summers are likely to be a little drier as we go through the century, assuming we follow that RCP 8.5 scenario. Now, when I show folks these charts, they often say to me, well, wait a minute, it doesn't rain very much during the summer anyway. Well, unfortunately, if we don't change our ways, it's going to be raining even less. Then when we get, back to fall, we're back at the pattern in which it's pretty much the same as historically. What you probably will see is that for our vegetation, this pattern is critical because whether we're looking at agriculture or forestry, it's during the summer and fall that the vegetation really needs moisture. And what we're going to see as we go through the century is less and less of that at exactly the time that the vegetation needs it. There's another pattern that we have seen historically and is likely to continue as we go through the century, and that concerns how the rain falls when it falls. What we're looking at here is a change in the pattern of precipitation. So as we go through the century, and this takes us up to the latter part of the century, again using the RCP 8.5 scenario, and that's the dark color, and the lighter color is the lower emission scenario. What we see is a reduction in the kind of light drizzly days, which are really great for replenishing soil moisture, but an increase in heavy downpour days. So that means the rain that falls is going to fall in really much more heavy downpours. And that has the consequence of causing soil erosion and landslides and floods rather than replenishing soil moisture. So the kind of rain that we're likely to be getting as we go through the future, into the future, is not going to be the kind of rain that's as valuable as that light drizzle is in terms of replenishing soil moisture. Okay, we're ready for another question, poets.
Yeah, we don't have any questions.
We're doing okay so far?
Yeah, we're doing okay.
Okay, we can keep going, and we will have another question break in a few minutes.
Mm-hmm.
Okay, so interesting question. What is our local climate history? Let's talk about that, and then we'll look at future trends. One of the things that most people who live in this part of the world realize is, if we look at the monthly precipitation, which is depicted here, January through December, what we find is most of our rain falls in the winter months. And when we get into the summer months of July and August, we really don't get much in the way of precipitation. And everybody knows that the temperature follows that kind of a pattern. And so what you can see is we live in a part of the world which has what's abbreviated conventionally as a winter wet, summer dry climate. Most people who live here really appreciate and understand that. But what is a little odd is if you grew up here, then there's a chance that you think that's normal. Well, it's not. It's a very unusual kind of a climate. It's called a Mediterranean climate. And this on the left-hand side now gives you a sense of what this thing I've just depicted is called a climograph. If we look at the climographs of New Orleans, of Boulder, Colorado, and New York, what you can see are very different patterns. Nowhere else in the country, besides the Western US, do we have this kind of Mediterranean climate. In fact, it's a pretty unusual climate as we look across the planet. It occurs in only 6 places. The European Mediterranean, duh, that's how it got its name. Southwest and Southern Australia. On the west coast of South Africa, Cape Town. You might have heard about Cape Town having some really serious water problems recently, exacerbating its Mediterranean climate concerns. And Western South America, and where we are here, Western North America. The Mediterranean climate has the consequence of producing a summer and fall which are very dry. So as we go through, and this is just the natural condition, as we go through the summer into the fall, soils and vegetation dry out. And that occurs wherever you go and find a Mediterranean climate around the planet. It's true for all of those places listed above. What that does, inevitably, is increase the fire risk. And when I say increase the fire risk, I don't say necessarily it increases the risk of a fire starting, although that could do, because we could be getting more lightning strikes. But what that does is mean that when a fire starts, the risk of it spreading increases because the vegetation is dry and ready to burn. And so that's one of the characteristics which is true of a Mediterranean climate. The second consequence of that, besides increasing wildfire risk, is these communities, these plant communities have evolved in these kind of climates. And so the vegetation in the Mediterranean climate system, wherever you go, that vegetation is the following 3 things. It's fire prone, fire adapted, and fire dependent. And that's important to understand because it means if we find ourselves committed to extinguishing or suppressing every fire that happens, what we're going to do essentially is destroy our forests. And that is to an extent is something that we're already doing because we've been imposing fire suppression for so long. I'll get to that in the last section. So let's look at historical data. Now, these are just the data. These are not models. These are data. This is what's been happening in Jackson County in terms of temperature. Okay, what we're looking at is Jackson County from 1900 to 2018. And these are compared to the 1901 to 2000 mean. That's what the black line is. And the blue line is a regression analysis through the data. And what you can see is over that period of time, Jackson County has been rising at the rate of about 0.2 degrees Fahrenheit per decade. Now, on the right-hand side, what we see is the same source of data. These data come from the National Oceanographic and Atmospheric Administration. The right-hand data are the data from Medford. They start in 1930, which is a little odd, and I don't know why this data set starts 1930, because our weather service at the airport has been collecting the data from much earlier than that, and I'll have a look at that in just a second. But what you can see in Medford is indeed the same pattern as for Jackson County as a whole, which is, of course, not a surprise. And what you see here is for Medford, the rising temperature has been occurring, that rise has been going on at the rate of 0.3 degrees Fahrenheit per decade. So these are the actual data of what's been happening in this area. This data set comes from our own weather service, and you can see basically the same pattern that we saw a moment ago, no surprise. But what's interesting, notice these data go back to 1912. That's when our own weather service started collecting data here. And this is Medford Airport, okay? But what I want to do is put in a horizontal line which depicts what are the criteria for desert. And what we can see is Medford Airport has experienced precipitation patterns which sometimes put us very close to being a desert. And you can see up to the more recent pattern that's happened a couple of times. Not so, maybe not so quite so frequently as we go back in history. So this again underlines the point that I was making earlier, that as we're going through time, the extremes seem to be getting more extreme. This is Medford Airport's mean annual snowfall. And you can see again, the trend is downwards. And notice again, a point that I was making earlier, as we look at the drop in snowfall seems to have started around 1970, as with so many of the climate trends that we have been seeing as they've actually been happening. Let's take ourselves up to Crater Lake for a moment. They have been collecting data, as you can see, on snowfall in Crater Lake since the 1930s, and these represent the annual snowfall at Crater Lake, and you can see again the trend up at 7,000 to 8,000 feet is quite parallel to what we've been talking about with snowfall again and again. It's dropping. That again becomes a problem when we start thinking about the importance of snowpack for our summer and fall water availability. In general, what we're getting is a slight difference in the snow and rainfall trend, as you have seen. The current trend is towards precipitation falling as rain at lower elevations rather than snow at higher elevations. Remember, snow, of course, falls during the winter, and the data that we were looking at earlier suggested that we're getting increased and are likely to get continuing increased precipitation during the winter. And this is what's going on. That snowfall is likely to be falling at lower elevations, but as rain. And this trend is expected to continue, as we will see when we start looking at the trends into the future. This is going to have an impact, not only on recreational activities. Think of Mount Ashland, Mount Shasta, and if you go further afield, you can think of Mount Bachelor and so on and so forth. This is Mount Ashland and Mount Shasta. Just nice photographs of those ski areas. Okay, we're on for a question pause again.
Yeah, we did have one question. They asked why focus on CO2, which is very important for plant life. Can't methane or even water vapor also be a greenhouse gas?
Oh, that question is very perceptive. It's very true that carbon dioxide is not the only greenhouse gas. It's the most important greenhouse gas because there's more of it. But methane and nitrous oxide and the chlorofluorocarbons are each of them much more potent greenhouse gases on a pound for pound basis, meaning you take a pound of carbon dioxide and a pound of methane and a pound of nitrous oxide and compare them. What we find is the other gases are much more profound in terms of the warming that they cause. It's very important for us as we're talking about the problem of greenhouse gases to understand that the other greenhouse gases besides carbon dioxide actually contribute something like 35 to 40% of the global warming. And it's unfortunate that many times folks focus on carbon and carbon dioxide. In relation to the other part of the question, it is true that carbon dioxide is a basic input into plants during photosynthesis. But in very few situations is carbon dioxide actually the limiting, if you want to call it, nutrient for plants. The most important limiting nutrients for plants are nitrogen, phosphorus, and potassium, which is why we have NPK fertilizers. Studies that are conducted on the response of plants to increased carbon dioxide, which are done in a greenhouse where they have abundant NPK, actually do sometimes show an increase in plant growth rate as a result of the fertilization, if you like, by carbon dioxide. Out in the big bad world out there, that doesn't happen so much. And in fact, some plants are better able to take advantage of the carbon dioxide than others. And for biological reasons that make it reasonable, the ones that do better as carbon dioxide goes up are the ones that are already adapted to very dry conditions. And those are the things we think of as weeds, exotic, invasive species. And so in the agricultural situation, it's probably the weeds that are going to do better than our crops. And there are other problems with the carbon dioxide is a plant food argument, which include the fact that the nutritional quality of crops seems to go down as the carbon dioxide goes up in the atmosphere.
Okay.
Okay.
So that was our only question, but we will have other opportunities to ask Dr. Ellen questions going on. So
and gosh darn it, if we finish a little early, we'll have plenty of time for a chit chat. Okay. So let's look at projected local trends in temperature as we go through the century. These are data from the U.S. Geological Survey, as I mentioned earlier. What these are depicting is the results of some 28 models. And what you can see down on the bottom left-hand side, the black area represents historical patterns, and the red line represents that RCP 8.5, which again, to remind you, was initially designated as the worst case scenario, but seems to be the trend we're on. And RCP 4.5 makes the assumption that we don't continue accelerating our use of fossil fuels and the resultant greenhouse gas emissions, but actually slow those down a little. And what you can see from these charts, and I should underline, the upper data set represents maximum temperature and the lower data set represents minimum temperatures averaged over the year as plotted. And you can get the mean projection by averaging the max and the min. And so what this is suggesting to us is by the end of the century, Jackson County is likely to have a temperature increase that's about, on average, 8.8 degrees Fahrenheit above the 1981 to 2010 average. And hold that thought, keep that 8.8 degrees Fahrenheit in mind. 9 degrees Fahrenheit is 5 degrees centigrade, and I'm going to show you some charts about what the implication of that is likely to be in our area. Jackson County precipitation projections. Remember, we looked at Oregon earlier, and this is very similar to Oregon as a whole. What you can see again is if you kind of put a line through that, what's the average precipitation, what you would come up with is something that's almost exactly horizontal, maybe a slight increase, but nothing significant. But you do see, as we go through the future, that same trend that I pointed out a moment ago, an increase in the peaks and troughs. The troughs are troughier and the peaks are peakier, if you like, which means it's the wet years are likely to be wetter and the dry years are likely to be drier. Same, we looked at snow for the state earlier. This is Jackson County snow, but it's measured not exactly in snowfall or snowpack, but in snow water equivalent. Except, unless you're a skier, in which case the depth of the snow is what's important, maybe the kind of snow. I'm not a skier, so I'm not familiar with that. But what we can see is, again, just as we saw before, snowpack decreasing from about the 1970s, but as we go through the century, likely to drop, and it looks as though as we are nearing the end of the century, following the representative concentration pathway 8.5 scenario, we're going to potentially have years where there's no snow at all, and on average we're down to maybe 10% of the snow that we have historically experienced. Certainly that's going to be a problem for ski resorts, but more profoundly it's a problem for downstream, for soil moisture and vegetation downstream. And this illustrates exactly the consequence of that. That soil moisture, as we go through the century, is likely to drop quite substantially in terms of the amount of soil moisture measured in inches, as you can see on the left-hand side, such that when we get towards the end of the century, the soil moisture will have dropped substantially compared to what it historically has been. Again, notice the soil moisture starting to drop around the 1970s. Okay, there's a quick question pause.
Let me check. Yeah, we have one question. Another one. Can you speak on the data previous to 1880 and comparison of models to that? Is the question.
Well, the people start in 1880 largely because that was then that the weather data were starting to be collected. I could talk about going back into the ice ages, but that wasn't a topic that was on today. That's an interesting question, and I'm happy to talk about it, but we probably don't have time for it today. And I didn't bring the slides to illustrate what's been happening as well.
That might be another program we could do.
Well, I'd be happy to do that.
Yeah. So that was the only other question that we've gotten. So.
Okay. Okay, good. Okay. Why should we care? This is the big question for me, because this is the question that really generated my engagement in this whole arena of climate science. My background is in teaching biology, and you're going to experience where that got me in just a few minutes. So I remember very distinctly several years ago teaching a course, and when I say several, I'm going back to the early 90s, teaching a course, an ecology course, and teaching a segment of that course which discussed the distribution, what influences the distribution of natural systems known in the biological arena as biomes. And just to explain what that means, a biome is simply something like a tropical rainforest, a deciduous forest, a coniferous forest, a grassland or woodland. Those are what we think of when we're using the word biomes. And you'll see what I mean as soon as I start putting these rascals on the chart, which I will do in just a moment. It turns out the two factors which determine where those biomes occur on the planet are temperature and precipitation, mean annual temperature and mean annual precipitation. It actually would be better to rephrase that annual average precipitation as water availability, but average precipitation is a pretty good substitute for that, and it helps us simplify the idea. So what we find is, if we look around the planet, these natural systems of biomes occur within that triangle of this range in terms of temperature on the vertical axis and precipitation on the horizontal axis. And what I'm going to do is flesh this rascal out. Up here, conditions don't exist. In other words, we don't have places that are very wet and very cold. They just don't exist. So this chart that I'm about to show you was modified from a character by the name of Bob Whittaker, who published this in a book, Communities and Ecosystems, in 1975. And I have taken the liberty of modifying it a little so I don't have to suffer from copyright infringement challenges. So when you think of basic climatic ranges, this is the designation. So at the top left, we're in Arctic or alpine situations. In the bottom right, we're in tropical situations. If we think of where we live here, and look at our historic temperature, these are our historic summer and historic winter temperatures, and this is our average temperature. Precipitation, and this is for that part of Jackson County where we live. We're pretty in the Bear Creek Valley. Bear Creek itself, down in the lowlands of the Medford area, we're at about 21 inches of rain a year. And so that puts us right about here. Okay, so let's now let's flesh this out with some biomes. If you think about the natural ecosystem that we live in, it's a woodland, shrubland, grassland area. Probably a perfect illustration of the natural vegetation for this area would be if you go down to, most people have been there, Emigrant Lake, and you walk around there, and you can see an oak pine woodland, and that's the kind of vegetation pattern or biome that occurred throughout much of this area prior to human settlement. And grassland would be also relatively common. So if we go up here, we're in the tundra zone, Arctic or alpine tundra. If we go down here, we're in a hot desert, little precipitation, and it could be hot, and it's going to be hot. We'll see that there are areas that have cold deserts in just a moment. If we go down to the bottom right, we're in a tropical rainforest. Okay, up here, as I mentioned, deserts are not all hot. The Arctic and Antarctic are actually cold deserts. Then we start fleshing this out with boroconiferous forest, tropical mountain forest, temperate rainforest, etc. And I'll just fill these suckers in for you, and you get a picture of where these biomes occur in relation to those two variables. Now, the important point to note is, with this chart, if you tell me anywhere on the planet what the mean annual temperature and mean annual precipitation are, we can go to this chart together and we can see what the biome, what the natural ecosystem will be. We can't figure out what the species will be, but we know essentially structurally what kind of a system it's going to be. We couldn't figure out the species because, as you'll probably appreciate, if you go to Australia versus South America versus Central Africa versus Southeast Asia, the species are different because they have geographical differences in the natural species. But we can figure out what the basic structural representation of that biome will be. But this is the thing that really got me concerned back in the early 90s when I was teaching a course. And I don't know whether this happened to me one day and I suddenly got whacked across the head by a 2x4, or whether it gradually occurred to me. But I was teaching this and I was reading about the projections from the climate scientists at that time. And this is the problem. If we take where we live now, right, where the little red X is, and we increase the precipitation, what we are doing is changing the climatic conditions such that the kind of biome that climate supports is going to be, the further we move, the more compromised it will be. Such that if we change the precipitation substantially from what it is now, what we'll be doing is shifting towards a temperate coniferous forest, for example. And one of the ways to think about that is to imagine this is what would happen if this is what will happen, the vegetation that we see as we go up towards Crater Lake, as we get into the more expansive coniferous forest. So that's the kind of change that we're likely to be seeing. The climate will change. We can't assume that the biomes can just get up and shift. That's not likely, as likely. Similarly, if we go the other way and decrease the precipitation, we're heading towards a cold, a desert-like condition. Remember, I showed that how the very dry conditions in Medford were very close to what kind of precipitation we'd get if we were a desert. By the same token, if we shift our temperature, now going down the chart, we're shifting it upwards. If we shift our temperature a few degrees, what we're again likely to be doing is making the climate substantially different from the climate that supports the vegetation that we now have, such that if we do that, if this climate changes where we live here, we increase our temperature some 5 degrees, what we're doing is shifting out of the woodland towards the shrubland, grassland, and if extreme, hot desert kind of a biome is what should be supported here. And the same is true if we were to go the other way. If we were to go into a cooling phase, we would be heading basically up the chart. This is airport mean annual precipitation in our area. And again, I put this back to remind you, in some years, historically, we have been very close to that desert-like condition. And remember, as we go into the future, the projections suggest that we're likely to have a greater frequency of those really dry years. So we are likely to be shifting from the woodland kind of biome climate towards a shrubland, towards a grassland climate. I'm going to show you a chart in just a moment, which asks the question, or tries to answer the question in terms of modeling about what the future is likely to hold across the planet. If we increase the carbon dioxide concentration in our atmosphere, on the left, we're looking at an 850 parts per million concentration of carbon dioxide. And on the right, we're making the assumption that we've done something to reduce the increasing carbon dioxide concentration in the atmosphere. Now, it's important to appreciate that these models are not focused on the carbon dioxide itself, but on the impact that that has on climatic conditions, particularly temperature. So in the chart you're about to look at, if you see an area which is red, the way to interpret that is that the biome that is there now, under the conditions that we're exploring, 850 or 550 parts per million, if the color is red, then the probability that that biome can exist there is 0. If we see blue, the probability is high. Now, this is an important component. The way these characters, Williamson and Jackson, conducted this study was they did it 2 ways. The first way, I'm not going to show you because it's not reasonable. The first way they asked, is the climate going to be existing anywhere on the planet appropriate for the biome that exists in any given place? And the second way they looked at it, which is much more reasonable, is will the climate that is relevant to the biome, let's take where we live here, is the climate going to be appropriate for a woodland within 500 kilometers, about 310 miles of here? And the reason that they picked that was because under natural systems, biomes can't hop on an aircraft and go anywhere on the planet. They are limited to the ability of the propagules or seeds that they produce. They limit the ability of those seeds to disperse. And that ability is very limited. And the way to think about that is think about a ponderosa pine tree and how far the pine cones can move. And the answer is they don't go very far. They basically fall underneath the pine tree. Maybe they spread a few yards either side. So the ability of a pine forest to shift naturally is very limited in terms of the speed at which it can shift. And so we're changing the climate over the next fewer than 100 years now, we're talking 80 years, substantially. And so it's not reasonable to expect biomes to be able to shift very much over the period that we're likely to be raising the carbon dioxide concentration as much as is shown. Okay, so here's the color code. Remember, it goes from red means there's no chance. and blue means the chance is high that these biomes would find a climate suitable for them within 500 kilometers. And what you can see looking at that chart is that the red color is spread throughout Africa, pretty much, except for the small blue spot in southern Africa. Throughout northern South America and through Central America is red. So those biomes are going to be in really bad shape. I just realized that the legend I put at the bottom is the reverse of the one I'm showing at the top. So that was worded a different way. So don't worry about the legend at the bottom. I'm sorry for that confusion. So this kind of condition would lead, this kind of part per million of carbon dioxide would lead to a warming of 5 degrees centigrade, about 9 degrees Fahrenheit. This one is much lower. So if we can control the warming of the planet, the survival of natural biomes somewhere within range of where they currently exist is not so severely compromised. And as I was, when I taught the course back in the 1990s, I didn't have this chart available to me, but the thing that struck me about the pattern we're seeing here is this represents a really disastrous future for our natural systems. What that means is the biodiversity on the planet will be seriously compromised if we don't do something to reduce the rate at which we are warming the planet. And the other thing that is important to realize, and I recognize that not everybody is as attracted to biodiversity as I am, being a biologist and teaching, having spent years teaching a course in conservation biology. But almost everybody is aware of the importance of eating. And just as we look at where the natural systems of the planet are threatened, what we need to do is realize that these variables that I've been talking about, temperature and precipitation, are exactly the variables that influence our agriculture, our forestry, and our fisheries. So if we compromise our natural systems, we're also compromising our own agriculture, our own forestry, and our own fisheries, and that's going to have a really dramatic and direct impact on us. And as you can see, which areas are most affected, and it's the tropics across the board here. Okay, so what? I just talked about this one, so we'll zip through that one quickly. Let's talk about wildfires for a moment, because that's something that's near to our hearts in Southern Oregon. And this is a piece of information that really surprised me when I came across it. The difference between a really bad fire year and a ho-hum fire year is only the difference of an average of 0.5 of a degree centigrade during the growing season from March to August. And 0.50 degrees centigrade is only 1 degree Fahrenheit. And so what that means is if we warm 1 degree Fahrenheit, we are shifting our climate towards really bad fire years, from ho-hum fire years, something which is a problem, not just because the fires destroy our forests and so forth, but also because of the smoke, as you can see, that it poses a direct health hazard to us here. Turns out the major factors influencing wildfire spread are temperature in the growing season, as you can see above, and the date of the spring snowmelt. And the reason that that's important is because the date of the spring snowmelt determines how much moisture there is in the soil as we go through the summer. One of the things that we have seen over the last few decades, and notice this again, as I've repeated several times, goes back to the 1970s when things really started to, if you like, heat up. What we're looking at here, and I'll just do a little pointer, is this is on the, if I can bring my pointer in here, this represents the period the wildfire period. And so back in 1970, wildfires started about day 150 of the year and continued up to about day 310 or so. As we go through the century up until the beginning of this century, you can see that the beginning of the fire season has shifted much earlier in the year, and the end of the fire season, when the last fire is put out, which is the black, end of the black, is later. So our fire season has expanded substantially over that period of time. Remember, that's when temperatures have been rising, snowpack has been declining, soil moisture has been declining. And in fact, it had expanded 2.5 months by the early part of this century. And that's the difference between that and that. But what's even more surprising is recent data tell us that the length of the fire season has actually expanded by 105 days, which is just about 3 months. Our fire season, to a large extent, and not entirely, but to a large extent as a function of the warming, has expanded 3 months, which is really troubling. In fact, as most people know, if you go down to Southern California, fire season is now 365 days a year, pretty much. This chart is a little complex, and so we'll walk through it rather slowly. What we're looking at here are acres burned, and the dark color is acres burned in drought years. The light blue line here is fire initiations by humans. The darker line represents lightning fire initiations. And here's the big message from this chart, which refers to lands managed by the Oregon Department of Forestry. The 10-year trend in the number of fires has shown some fluctuation, but on the whole, pretty level throughout that period of time. On the other hand, if we look at the 10-year trend in the areas, acres burned, what we find is a considerable pattern. Down here on the right-hand side, you can see maybe something of a slight increase in acres burned. And this is the one that most people who live here really are so conscious of. It looks, certainly if we go back to the 1980s, it looks as though we've experienced a quite dramatic increase in the areas burned by fire. And it's not that it just looks like that. That does seem to be what the data suggest. But the thing that is quite surprising to most people looking at this chart is to go back to the beginning of the last century and see the acres burned back then. And you can see it's actually much higher than what we're experiencing today. So it's worth asking what's been going on that might have been influencing this. There's a phenomenon called the Pacific Decadal Oscillation in temperature, which is an oscillation in temperatures around the Pacific. What was happening during the period 1920s to 1940s, we were in a warm phase. A warm temperature phase increases evaporation, and so soils and vegetation dry out, and so it's reasonable to think, okay, that's possibly a major cause for the large number or large extent of wildfires back then. Another thing happened, however, which makes this really problematic, was in 1944, that wonderful Smokey Bear campaign really kicked off and was very successful at suppressing fires that started. As that happened, the Pacific shifted into a Pacific Decadal Oscillation cool phase. And so over that period of time, for the next, 20 or 30, 40 years, we were in a cool phase and we were massively suppressing fires, and the areas burned really dropped. So it's not easy to determine whether it was the fire suppression or the climatic shift that results in that drop in areas burned. Then we get into the early 80s, late 70s, and the Pacific decadal oscillation switched back to a warm phase. And remember, again and again, we've seen this, global warming started really to have a profound effect around the 1970s. And since then, the area burned by fire has started to pick up again. Now, some folks, should point out, will argue, and it makes a lot of sense, that one thing that happened was with the success of Smokey Bear suppressing fires, our forests were invaded by large numbers of Douglas firs. And so when we go out into the forest now, if they haven't been thinned, we find a lot of very dense Douglas fir, which have the impact that if a fire starts, they become a real serious fire hazard because fires whip through them and get up into the canopy and cause all kinds of severe fire problems. But there are other problems that are related to all of this. This represents the historical distribution of Douglas fir, and the left-hand chart is the whole of Oregon. The right-hand side chart is just the bottom southwest corner. And so we're in the Medford's in the Rogue Valley over here. So and so that's grassland at the moment. But you can see Douglas fir now are pretty viable. So over here is the viability score. The darker the red, the more viable are climatic conditions for Douglas fir. And so what this is doing is illustrating the problem that I talked about earlier about climate influencing forests. So this is high viability, low viability, and this is absent. So as we look at the climate models, using again that RCP 8.5 and go through the century, what we find is the climatic conditions vary such that the viability of Douglas fir is going to be substantially reduced. So Douglas fir is the most important commercial species in our forests, and so that's going to have a really profound impact on timber industry. It's always struck me as being remarkable that folks in the timber industry seem the least aware of the impact of climate change on their livelihoods. If we look at the ponderosa pine and the Gary oak, let's see what's likely to be happening to them as we go through the century. Ponderosa pine, again, looks as though its viability is going to be substantially compromised as we go through the century. And the Gary oak, the green represents suboptimal climatic conditions. And so it looks as though the Gary oak is also going to be compromised, although the range of conditions under which it could live will be expand, optimal conditions will climatically decline. The lodgepole pine is a fascinating example. And over here, we see the current distribution of lodgepole pine. And look at 2030, 2060, and 2090. Lodgepole pine is a very important commercial species in some parts of Oregon. And yet, the climate, by the end of the century, climatically, Oregon is likely to be outside of the climatic range wherein the lodgepole pine can be supported. This is lodgepole pine again. Middle is Sitka spruce. Sitka spruce probably eliminated. Western hemlock substantially contracted in the area that it can survive. So the message that I'm trying to convey here is we really should care about what's happening to our climate, because it's not only going to compromise, if not totally devastate, our natural systems, our forestry is going to be really likely to be severely compromised. And I'm just going to say a last couple of words before we wrap up for the last question or two about the economics. One of the things we often hear folks complain about is the cost of reducing our emissions. And I'm not going to pretend that that addressing our emissions would be totally benign, because some folks are likely to be disrupted in terms of the livelihood they're engaging in. If you're involved in fossil fuels, for example, that's something that we really want to get away from. But, and this is the important point, if we destroy our forests, our agriculture, and our fisheries, the economic cost of that is probably incalculable. And because without food, without fiber, I mean, what is that? So the problem that we face if we don't address global warming is we really are likely to compromise life as we know it, if not life as a whole, for our kids, our grandkids, and so forth. And that's it. So if you have any questions we don't have a chance to answer, please shoot them at me. I'd be more than happy to try and answer.
Yeah, it looks like we're at 3:12, so we just have about 3 minutes left. We don't have any additional questions that have come in. Did you have another slide to go through, Alan?
No, this is the end of the slideshow, and if anybody wants any further questions, if anything occurs to folks, please shoot me an email at alan@socan.eco. I think Kevin did that last time. And just make a point, next time I'm going to talk about individual and collective action to address the climate crisis.
We did have one more question come in. It says, can you address any ocean issues?
I can, and we'll do this in 2 minutes. The big problem with oceans, certainly oceans are warming up, and that compromises in the same way that warming conditions compromise terrestrial communities, so they do marine communities. But the big problem oceans face is that the increased carbon dioxide in the atmosphere dissolves in the ocean and produces carbonic acid. So our oceans are being acidified at an alarming rate, to the extent that already oyster fisheries are off the coast of Oregon and Washington are being seriously compromised, because the larvae of the oysters in the acidic conditions just can't grow, and so they're just eliminated. So it is very serious, and that on top of the warming, ocean acidification is causing and will continue to cause a serious problems, even more compromising, of course, our fisheries.
Thank you. I think that's our last question. Thank you, Dr. Allen, for sharing with us today. For the August 18th program, you can register for the program at jcls.org under programs and events. Just find the one for our August 18th. And you can register there to get the Zoom meeting details, and also the Jackson County Library Services. We have a lot of resources, digital and print. If you are interested in this topic, you can research them there, or also attend Alan's last program of his 3-part series. So thank you again for coming.